In this video, we'll investigate symmetry and even and odd functions. The first thing I'd like to discuss is the idea of symmetry. And when we talk about symmetry, we're talking about something that is the same on both sides of something. So in this particular case, this first example, we have symmetry with respect to the x-axis because this function is symmetric about this line here. So that means that if I have some ordered pair x, y, then I'm also going to have the ordered pair x, negative y. If I have symmetry with respect to the y-axis, it's going to be symmetric to that axis there. And if I have some ordered pair x, y, I'm also going to have the ordered pair negative x, y. Lastly, if I have symmetry about the origin, right here in the center, that means that if I have some ordered pair x, y, I'm also going to have the corresponding ordered pair negative x, negative y. So we can see those graphically, typically. I like to think of folding on a particular axis. So if I fold it on the x-axis, does it land on itself for this one? If I fold it on the y-axis, does it land on itself there? And for origin symmetry, I have to think about folding it on both axes. So if, for example, I was folding it on the y-axis first, it might look like this, but then once I fold it on the x-axis, it's going to be exactly what I started with. So we have some algebraic tests of symmetry. If we want to find out if a function has x-axis symmetry, then we're going to replace our y with a minus y. If we get an equivalent equation, then we have x-axis symmetry. So to find x-axis symmetry, we replace y with a minus y, and it should be unchanged. Similarly, to find y-axis symmetry, we replace x with a negative x, and we get an equivalent equation. Then it has y-axis symmetry. And for the origin, we need to replace both x with negative x and y with negative y and get an equivalent equation. It doesn't change. Then the graph is symmetric with respect to the origin. This will also be, let's go back and look at our picture, a rotation of 180 degrees. So we could take this and this here and rotate it around 180 degrees and it would look exactly the same. Okay, let's look at a couple of things. One, let's just talk about an ordered pair, -5, -6. So we're going to assume a standard scale. 1, 2, 3, 4, 5, and then up 6. Our point is right here, so -5, 6. If I have x-axis symmetry, and remember this is our x-axis here, then I should be able to replace y with a minus y and get a new ordered pair, -5, -6. If I want this ordered pair to have y-axis symmetry, then I can replace x with a negative x and get 5, 6. And lastly, if I want to have origin symmetry, I want to rotate 180 degrees, or I can replace x and y with their opposites, 5, -6, And that's going to put me right here for origin symmetry. So how do we look at an equation, because we can look at the graph pretty easily, and test for symmetry with respect to the x-axis, the y-axis, and the origin? So I am going to, for each one of these, test for x-axis symmetry, y-axis symmetry, and origin symmetry. So we know that for x-axis symmetry, we want to replace y with a minus y. That is now a different equation, so it does not have x-axis symmetry. If I replace x with a minus x, on the other hand, minus x squared is just the same as x squared. And so we do have y-axis symmetry. And if I replace them both, we can see again that it's changed because of this, and we do not have this. So in this particular case, we have y-axis symmetry. All right, let's look at this linear equation. This is example B, 2x minus 5 equals 3y. So if we want to test for x-axis symmetry, we're going to replace y with a minus y. And that's going to change things. So that is not symmetric to the x-axis. Similarly, if I replace x with a negative x, we do not get the same thing. So it does not have y-axis symmetry. If I replace x with a negative x and y with a minus y, we're going to get negative 2x minus 5 equals negative 3y. And if I wanted to see, it's a little easier here. If I multiply this whole thing by negative 1, I'll get 2x plus 5 equals 3y. And so it also is changed, and we have no symmetry here. Let's look at example C. Testing for x-axis symmetry, I replace y with a negative y. That's going to change things. Replacing x with a negative x, I'll just get 4 over x. That also just changes things. If I replace y with a negative y and x with a negative x, I get negative y equals 4 over x. And if I multiply this equation by negative 1, because as long as I do it to both sides, it's not changing the value, I get y equals negative 4 over x. So we do have origin symmetry on this one. All right, lastly, we have this equation, and we want to check for x-axis symmetry. So we will replace y with a minus y. And you can see that because I'm squaring a negative, it just becomes 2y squared again, and I do have x-axis symmetry. If I replace x with a negative x, the same thing happens, because when I square that negative, I just get positive x squared. And of course, if I replace them both, the same thing happens again, and I have origin symmetry. So I have all three kinds of symmetry here. So what constitutes an even function and an odd function? Well, if we have a function that is symmetric with respect to the y-axis, we say that this is an even function. That means that if you replace x with minus x, you'll get the same thing. This is something like f of x equals x squared, we know that that's the parabola and that it's symmetric to this y-axis. But you should pay attention, this is an even number. If we have a function that's symmetric to the origin, we say that this is an odd function. That means that if we replace x with minus x, we get the opposite of f of x. So that may be something like x cubed, which has this shape and is symmetric to the origin. And you should pay attention, this is an odd exponent. Let's look at the first few as graphs. So this first one has no symmetry. So it's not even or odd. The second one here is symmetric to the y-axis. So this is an even function. Over here we'll say this one has neither. This one here, you can see if you rotate this 180 degrees, that it will land on itself, which means that we have symmetry with respect to the origin, and so this one is an odd function. Similarly, this is symmetric with respect to the origin. This one is also odd. This last one, or number 5, certainly if I fold it on the y-axis, it's not going to have symmetry, or the x-axis, it's not going to have symmetry. But if you can visualize what this would look like rotated around 180 degrees, keep in mind that this high point here is going to be down here. So it's going to look different. And so this is not symmetric to the origin either. And so we say neither. All right, number 6, we can see by the graph that it's symmetric to this y-axis. And so this graph here is an even function. So how can we determine algebraically if a function is going to have symmetry without doing the symmetry test? In other words, is it even or is it an odd function? And this really has to do with these two graphs that I wrote up here. These exponents, we know that if we plug a negative value and we raise it to an even power, it does not change. But if we raise it to an odd power, it changes its sign. So when we look down here, we really want to look at these exponents. So we know that this is x to the first, and every single one of these exponents is an odd number. This is an odd function. Over here, we might think of this as x to the 0, and although 0 is not even or odd, it's in the pattern of the evens. And these are all even exponents, so this is an even function. If, on the other hand, we have a function that maybe has some even and some odd exponents, like this is going to be neither even or odd. That concludes this video on symmetry and even and odd functions.